So super excited to have the opportunity to have a dedicated session to this. I'm sure you'll talk about your background in the presentation, but you work at Moody's and you have experience in various different languages, and you've been doing quite a lot of work with Rust. So Laura, take it away.
Yeah, thank you. Yeah, it's quite interesting, this whole topic, because I actually came to learn Rust relatively recently speaking. Probably when I started this role, it became a requirement, and now more and more I'm doing that, and I'm also realizing actually this is a really fun language. So my background's actually Python, and you don't need to worry about a lot of things with Python. The types are dynamic. The memory allocation is all over the place, and you don't need to think about these things. But yeah, Rust, sometimes it kind of, when you first look at it, you think, oh, it's not going to be that bad. It's just a bit more thinking, but then it throws you as a Python developer just totally off your horse. And I think this was one of those things, exactly understanding how scope, borrowing, and borrowing works, and lifetimes, just when I first read about them, just couldn't get my head around it. And what I also found interesting while I was doing it, it came up a lot, actually, when I was doing a workshop on threading. That sparked this whole conversation. So I thought, well, okay, I have to include threading in this. So yeah, so let's go through this. The plan is to also do some code examples here. So we'll walk through some theory and then also walk through some practice. So basically, they do say it's an excellent practice to have a few take-home messages. And I think these are the ones that I'd like you to have. So if you've used Rust, what you'll know, first thing you'll learn, is that variables, whether they are stored in stack or on heap, they live within scope, and they are dropped when the scope ends. They are no longer accessible. And so the other thing we have is references, because there is ownership, of course, for variables. So the only way for a variable to be changed is if the scope actually owns that variable. But what if we want to just see the value and use it in use it in calculation of something else? So that's obviously a reference, and we can pass those along different scopes. However, they must live within that scope. And obviously, if so, what happens with Rust is that if you have a reference being called, but the value that it borrows from has been dropped, you'd have a dangling reference. And actually, that's the kind of interesting thing I've found about compiled languages, is it doesn't allow you to do that. So I think you would have seen that immediately as soon as you start writing Rust. When this gets interesting and complicated is when multiple references and structs get involved, because of course, different variables will have different scope lengths. They might live for different amounts of time, and also same with structs as well, and functions, and how all of that gets together. That gets complicated. So how do we and the Rust compiler make sense of all that mess? The answer is lifetimes. Basically, that I think that helps to remember that it infers relationships between references. So let's have a look at actually how to use it in theory and practice. So you can see that actually for a single reference, it's fine as it is. So you don't need to worry about lifetimes. because basically Rust can figure out, okay, one reference, this is where the value comes from. Is it in scope? Yes, it is. Okay, it's fine. I don't need to worry about it. However, if it needs to look at multiple references, then things like lifetimes and lifetime bounds come in. So let's have a look at how that looks into practice. So if we have, so this first function is a single string function. And what we have is we take a reference for string and we return a reference for string. So we just, that's all we do. And here, Rust can figure it out. It doesn't really have to think about these things. And you'll see this lifetime Ellison kicks in. We'll talk about that in the next slide, about exactly what that does. However, when you have more than one reference, so these are pretty much identical in a sense, right? They could be defined at the same time, but they could not, right? They're both strings, but they need to be tied together. So Rust needs to know, okay, this lives for the same amount, for at least for the shortest amount of time. And if you want to see exactly how that looks like, you can uncomment to see the error. So I forgot to mention, this is a part of Rust Workshop repository that I've submitted to my GitHub, and those will be shared later. So you'll be able to play with all of this. So let's have a look at how does that actually look into practice. What we have is this get combined string. So does anyone have an idea of what the single string is going to be? I think that one's quite simple. It's just whatever string 3 is, which is your Rust code. So, but what happens with combine? So we have combine, and basically it returns whichever of the X and Y is longer, right? So we have string 1 and string 2. So all of this is defined in the same scope. And yeah, let's see if this compiles. Okay, so let's learn about lifetimes. This is the first function. Second. So the single string is your Rust code, and the combined string is equals awesome instead of Rust, because equals awesome is longer. So that's quite simple. And therefore, you know, whatever you write is actually awesome. So basically, that's how that would work in a function. If we go further in the slides, I also mentioned they are essential when creating struct with references, and that can happen for various different parts. So first one, implement block. So we have content, which is a borrowed string. And when you implement something, for example, a new function or a display function, I tried this, I actually tested this. It's impossible to create a function for a struct with a borrowed value without defining a lifetime, even if it's just one function, even if you just return something, because I suppose it's because it needs to know that both the borrowed thing and the struct itself will survive long enough, because otherwise you have document, but if the content is dropped, then you know there is an error there because you can't access the content anymore. So in the meanwhile, author, which is a string, so an owned variable, this is something that's going to be owned by the struct, that doesn't need a lifetime, and it can quite happily go on its own. And so as we can see, lifetimes, very importantly, they are denoted by these guess, yeah, like uptick, an uptick and a letter. So normally people use things like A, B, whatever, but there are no strict rules on what you need to name them. I guess otherwise it becomes just very verbose if you make those longer. There are a couple, I think, special cases. There's at least one which we'll mention a bit later as well. So next function is create document. So let's see how you can create a struct and display what it does with this. So as you can see, that has compiled and shows it quite successfully. And last one in for again continuing to work on our trait. Same goes here. So our document has an extract trait, which does pretty much the same thing as the content thing. Again, also, since it's has the same sort of problem, it also needs lifetimes. And if we run that get document extract, we get extracted important Rust document. So are there any questions so far? Okay, so
I don't think there are any questions so far, but maybe, yeah.
Yeah, no worries. I think there might be some more after this one, because this is where a lot of those concepts come together. So I think where it becomes really tricky, and I actually spent a lot of time wrapping my own head around it, is how it works when struct is called in a function. So this is a new struct wrapper with a borrowed string, so very much similar to the document, and we have a couple of implement functions. So this one's pretty self-explanatory, but this one is where actually things become interesting. So what you meant to make sure is that whatever comes out of the combine function survives at least as long as the struct itself. So that's why A is associated with the wrapper, and that's also the lifetime for the return function. However, B is something different. So other is a string that comes in from outside. It's not part of the same struct, so it gets a different lifetime because its value could be dropped independently of the wrapper. And yeah, initially when I was looking for examples for this tutorial, it said, oh yeah, this is fine, you can do this, you can run this, it's okay. However, it turns out there also exists these things called lifetime bounds. And for this one, you want to make sure that B lives at least as long as A, or in this case, you write this where B outlives a lifetime bound. Without it, it doesn't compile. So actually, compiler is really quite smart. And if you have the lifetimes added, it will start to figure out the relationships and say, well, this doesn't quite work. We want to make sure that the second reference is working. On how, so this is the example of how that works. So we have string 1, which is put into the wrapper, and string 2 is our static borrowed string world, and that is added to the combine. So that's basically our combine thing. And what you can check is whichever one of them is is longer, right? And that's going to determine what the function returns. But what is important is that it has that the value of b, it has to be at least as long as a, because imagine if you don't have if this string for some reason is dropped when you call this, you're going to run into a problem, because what are you going to run the reference to? So the lifetimes of both of these have to sort of be tied together, and this is what that specifies. And if we run the final one, and the combined one is world, so we are able to return this other string. And that basically goes over the sort of normal ways you'd use lifetimes in regular functions and also in struct. One more thing, just a very special case, is static. It's possible to denote a string static, for example, and it's a special case where it's valid for the entire program duration. It's used for global constants or string literals. And this means that the data is stored in the program's binary and never deallocated. So a couple of reasons why you want to be careful with this is you can have over allocation of memory. So if you just use it within a small scope, you don't want to set it as static, because you want to have it, use it, then let it drop. And also, if it's used for strings that actually do get dropped, that would cause errors, as you can imagine. Okay. Okay. Sounds good. Sounds so good so far. So I did mention that Rust is actually quite smart. And the reason why it is quite smart is because it has the lifetime Ellison. And so what does it mean? So each reference gets its own lifetime. And if there is only one, the output reference gets the same lifetime. That's why in the first reference, the first function that I had as an example, we didn't have to specify lifetime because it automatically figured it out. And if there are multiple references, like in that case with our structs that get implemented, and one is self, it gets the same lifetime as self. So we do not associate extra lifetimes with the self, because it's automatically assumed to be the same as the lifetime of the struct. So you can kind of see that here. So wrapper has this A, and so this is also A, the self, and the output is A, because that's what the self is. This one is different because it comes again from outside of that initial scope, and that's why it gets a separate. That's again the rule for lifetime Ellison. Different references get different lifetimes. Cool. So, what could go wrong? So these are some of the examples of what happens. Of course, so if you try to return a reference to a local variable, well, it's going to get dropped, and you're not going to be able to use that. So a way to fix that is to return actually like something that is owned, such as a string. So you don't return a reference if it's owned within the function, within the scope of the function. So yeah, really need to think about how you manage that scope. Not that, again, a problem that you probably wouldn't have in Python. It would be totally quite fine to return whatever you define within the function. And so this one was quite interesting. So mismatched lifetimes. So I ran this from a tutorial example and actually got an error and thought, so if you run it so that it returns other, it says, oh, method is supposed to return lifetime with lifetime A, but it's returning one with a different one as it's defined here. And what I do like about Rust compiler is that it actually does say how you can fix it. So here it says you can fix it by adding a lifetime bound, which specifies that the other, so lifetime B, needs to outlive lifetime A, or otherwise, it might get dropped. A couple of things on best practice. Lifetimes, it is sort of a sticky subject, and what I'd say is the easiest thing is just really try to look at the examples, try to run them deliberately, causing errors and trying to understand, okay, why these errors happen, and always think in terms of scopes and ownership and borrowing. So is this thing still within scope when I'm using it? Is it not? And that really helped me to understand the subject better. And yeah, so rely on lifetime elision, I guess, when you can. Keep your reference relationships clear, as you saw, using different ones when they are in different scopes, and do not use static unless absolutely necessary. So only when working with global or constant data. Okay, so we've gotten through lifetimes of borrowing, and we've gotten to the actual threading part. Any questions on the lifetimes?
I do, but we can keep it to the. Oh, go ahead. Wait. Oh, yeah. Sorry. How do you determine to use lifetimes versus copying? How do you do? When do you use one over the other?
Okay. I guess that's a good question, because when you copy the value, don't you?
Yeah.
So it depends on whether or not you want to consume the value. If you lifetimes you'll need when you deal with references, whether or not they're mutable. I think copying is a more, okay, you actually want to take ownership and you want to leave the original reference and the original thing the same. At least that's how I'd use it, but yeah, I haven't come across that much. I mean, in general, they do say avoid copying in Rust as much as you can, because it's there's so much focus on having efficiency, right? And copying is reducing that efficiency. Although that's not to say that that's not that it's not allowed to be used when it's necessary.
No, of course. No, I just use copying, I think, a little too much. So this is good. This is good.
Well, that's fair.
I think it's always tempting to use copy, but I think broadly, when you're working with types which are cheap to copy, integers or a Boolean or something like that, then yeah, I think that's okay. But when you're copying a big strut, then you must think,
yeah,
should I?
Yeah.
Yeah, okay,
exactly. That's a good way to think about it. The sort of memory part of it. If it's a small thing, then cloning is fine, or copying indeed is fine. For bigger things, you really need to convince yourself that there's no other way. And yeah, we'll sort of have a bit of a look Not really, but yeah, it's quite interesting for cloning with Arc, which I'm gonna touch later.
We've got another question from, is it Bhavani? Is that how I say your name?
Yeah, that's right. Thank you for the examples along with the presentation. I think that really helped. Out of interest, do you know if there's any tools, plugins, or something that can also help you visualize these lifetimes? Because that's really a good way to think about it. When you used the bound, B must live as long as A.
Mhm.
I'm wondering, other than the Rust compiler telling you, if you know of any.
Yeah.
That's a cool visual.
Oh, that would be amazing. I
Right?
don't know of any,
Okay.
but perhaps people in the community will. I
Maybe
think
Caroline knows.
amazing idea.
There is, if you use VS Code, there is a plugin called Rust Owl,
Oh,
like the bird.
okay.
Mhm.
Okay.
As far as I know, it only works in VS Codes, and it literally, if you configure it kind of as it should, it will show you how, well, it will like annotate on your code where the lifetimes are.
I see. Thank you. Awesome. Thanks.
Okay. So yeah, I don't know. Do we have time to quickly go through threads? Do let me know if I'm running out.
You've got 15 more minutes, so I think we want some time for questions. So yeah, I think you've got time. Yeah.
Okay. Yeah. So try to go through it quickly. So threads. Basically, very quick intro to the fact that Rust does allow computation to be split in threads, and I do not want to go into too much detail into exactly how threads work, because that's a topic for a whole different workshop. But basically, it does allow you to do that. There's a library, and of course, pros, you improve performance, and cons, you improve complexity. So again, this came out of something that I did for a passion project of mine, tried to get threads working and got very confused with how move and everything works. So again, this goes back to the whole idea of ownership and borrowing. So if for those of you in the know, of course, move means moving ownership from one thing to another. But how you can actually do that in a way that doesn't make you lose your mind. Get onto an arc. Arc is basically atomic reference counter. So basically, you can define a variable on it, and as long as, and what arc does, it ensures that at least one thread holds a reference to the data, it won't be deallocated. And it counts references and make sure they can be used across threads. And since it knows, for example, if you have four threads, you have 4 references and then your main reference. So until all of those 4 references are dropped and the main reference is also dropped, the value is not going to get deallocated. So basically you get quite a safe way to pass values to threads, because otherwise, if you don't keep track of your references, might get lost. And yeah, so the way it does it is more or less via cloning. And what it does, it doesn't clone the data itself, but rather a reference to it, and increases the counter. So we were just discussing right now, copy versus reference. So this is why I mentioned cloning. Cloning is extremely cheap, as it only increments the reference count. It only shares references, and if you've looked at your data stock, just know it's extremely tiny amount of memory that needs to be shared. Things to note: it's only for sharing immutable data between threads. And we'll look at how to do things for mutable data next. But let's start with arc. So let's move over to threads. And what we want to learn is about threads. I'll run the card. Run. Okay. So just to get just introduce people, this is how more or less a simple thread looks. So this is the main part of the function. You know, pretty standard stuff. But this is where interesting things happen. So you create threads, in this case 10 threads, no, 9 actually, outside the sort of main thread. And what this means is that you can more or less simultaneously do work. So this relies on computing processes. So if your computer has, you know, more than one core, you know, each of these can be run on different cores. What you also need is you need this handle join. Otherwise, you get quite an interesting thing where once main thread work is done, so this would be done in, let's say, 5 milliseconds, but this would take 10 milliseconds. It would finish, it wouldn't wait without the handle join for the rest of the stuff to finish. So do be careful. And, you know, if you do get your hands on this repository, try out moving this around and, you know, commenting it out, adding it back in, and basically see what happens. I think that's a really fun exercise to get your head around threads. Okay, enter arc. So this is pretty much very similar. We don't really have that much going into main. So in main, we have our counter, and so that's arc. Arc is basically taking in just a literal 0. It's not very interesting. To be fair, we can make this perhaps more interesting and give it a 10, because, you know, we are all 10 out of 10. And this is basically where the handles are stored. And what we see is for each thread, we have we clone arc 10 times. And remember, this clones the reference to the original stuff. So it's going to be a reference. It's going to be a reference to that value number 10. And it is, yeah, immutable. We'll see basically what happens. And so this, since we have the handle join, it will make sure that all of the handles actually finish working before we before finished. Okay, so this is the spawned main thread, the single thread, and this is going to be the end arc. Oh, sorry, I forgot to save before I ran. Yeah, this should be 10, basically, if I would have saved the file. But if you remember, it was initially 0, and this is indeed what you can see. Counter value in thread is 0, and it is immutable because basically nothing happens. You can't change it. But if you need to do a lot of stuff in a thread and clone something simply and quickly, that's the way to do it. But what if you want to actually mutate your data? Mutex. It's quite an interesting actually type of data within Rust, and yeah, not going to go super deep into it, but it's it basically makes sure that only one thread at a time can access the data that it wraps, and that prevents data races if used correctly. So it's locked with the lock function, and the lock is acquired if it's available and released when it goes out of scope. So we'll see that, we can have a look at how that works in like a thread. What I found really funny was that if thread panics while a lock is being held, mutex will become poisoned and you'll get a poison error. I really want to see that, although not in production. Something to think about is avoid causing deadlocks, and so you need to make sure that locks are being released appropriately, so that scope is being dropped and you don't have two things locked at the same time. And the way to get it to work with multiple threads is to use an all thread arc so that it can be shared across multiple threads. How does that look into an example? So enter mutex, very similar to what we had before. So we have a counter, again arc, again 0, but on top, but instead of just a plain integer, we have mutex here. So we once again clone it, nothing changes. But here something different happens. So we have mutex guard actually once the counter is locked. So this means no other thread can change it. And then unwrapped. So that gives you the mutex guard. Mutex guard implements the deref trait, which allows basically things to be changed. And as we said, you can see that the scope ends here. At that point, the lock gets dropped, and the next thread can pick the counter back again and change it. Yeah, the rest of it is pretty much same normal boring thread stuff that we looked at already. So how does that work? So we have our final result, which is 10. So we started with 0, and it went 1, 2, 3, 4, 5, 6, 10, and it gives you 10. So this one, you'll notice I didn't actually change. And you can also do a very similar thing for vectors, which is slightly more complex, but it's pretty much the same sort of thing as as with the integers. Ooh. So that's more or less how the resulting vector looks like. So this is quite interesting because it's pushed it at various different indices, so it looks a bit weird. And one of the challenges I have for you, if you choose to accept it, is to modify this code so that each thread updates a different index in a vector, and it doesn't look like a random code that you can use as your password. And with that, I'd like to thank you all for listening to me, and yeah, I hope you enjoy also looking through these wonderful references that have helped me to put this together. And yeah, thank you all very much.